Hello. So my name is Nishchal Dinesh, and today we will be talking about our mini project 3, which is HDL implementation of a LeNet Inference engine for MNIST Digit Recognition. So this is for our subject, Digital Design for AI and DSP, EE278. So let's start off. So what we'll be looking in today's presentation is, first of all, introduction to what the project is all about, what the task is, what is LeNet 5, what is MNIST, the methodology and the hardware implementation for implementing this particular task, the results, and the conclusion and future scope of this project. Let's start off with introduction. So the task involves implementing the forward data path of LeNet model in hardware using Xilinx Vivado or Vitis. In my case, we're using both Vivado and Vitis. Vivado for comparison between the different boards and Vitis for getting the final output. So a couple of things is we're using LeNet architecture. So what is LeNet architecture? It's the forward data path that refers to the processing input through the layers of the LeNet model to produce outputs, basically predicting. And you have half precision floating point, which is FP16. So this refers to the 16-bit floating point arithmetic for multiplying and accumulating operations, which is MAC operations. So why do we use half precision? It basically reduces the hardware resource utilizations and power consumption while maintaining the same level of accuracy, especially for machine learning tasks. Bit accurate half precision max. So we had previously developed Mac units, FP16 Max, in our previous mini project 1 and 2, and continuation 2, we're using it to implement operations like convolutions, matrix multiplications, and ensuring bit level accuracy. So final task to develop hardware descriptions for LeNet forward path using HDL. Start off with what is LeNet. So LeNet Inference Engine refers to the implementation of convolutional framework or a software tool that can perform inference using the LeNet architecture, basically for CN, which is convolution neural network. So in LeNet architecture, it's one of the earliest convolution neural networks and is primarily used for handwritten digital recognition, like MNIST, which we're looking in the further slides, or even in some cases, simple image classification tasks. So it has convolution layers, and you have pooling layers, which reduces the spatial dimensions, fully connected layers, which performs classification based on extracted features, and activation layers. And in our case, we'll be using the ReLU function, which is rectified linear unit. Basically, it replaces the negative values with 0. You have an inference engine, and inference engine basically takes a pre-trained model like LeNet and applies it to a new input data for predictions. So this is the architecture of LeNet. So you have, as you can see, the input is 32 into 32-bit image, which is 108. And you have, the first step is you have 5 into 5 filters, which basically convolution happens. Then you have sampling, where that's basically pooling. Then you again have convolution, which again includes 5 into 5 filters. Then again you have pooling, which is subsampling. And then finally you get the Gaussian connections in the end, basically giving you the final output. So now what is MNIST? So it's basically the full form stands for Modified National Institute of Standards and Technology Database, and is a widely used data set in machine learning and computer vision for training and evaluating models, especially for handwritten digit recognition tasks. So the data set consists of it's basically pre-written data sets. So you have data sets consist of grayscale images of handwritten digits 0 to 9. And each image is 28 into 28 pixels with values ranging from 0, that is completely black, to 255, which is white. So you have 60,000 image, which is your training set, and the test set is 10,000 images. And it's usually used for machine learning tasks. And each image is represented by a 2D array of pixel intensities, and they're labeled in 0 to 9. So that's layer 0, layer 1, layer 2, 3, goes on to the layer 9 for each image. The image are already size normalized and centered in a fixed size 28 and 28 grid, simplifying the pre-processing step. This is how an MNIST dataset looks like. So as you can see, label 5 is labeled for the digit 5, 0 for 0, 4 for 4, and all of them are 28 and 28 images. So in our implementation, we're using ReLU function. So what ReLU function is, basically it is f of x is equal to maximum of 0, x. And it basically replaces all the negative values with 0. And it's basically, as we mentioned in previous slides, it is basically known for rectified linear unit. And the graph shape here, you can see, starts off as a flat line for x is less than 0, and a diagonal line when y is equal to x. So any positive numbers from 0 and up is x is equal to y, whereas any negative values, y is equal to 0. The main use is ReLU is widely used in activation function neural networks to introduce non-linearity and to speed up the training. So you don't have to take care of any of the negative values. So range is from 0 to infinity, making it unbounded for positive inputs. So the methodology which we are using for our implementation is you have a 32 to 32-bit input. So why 32, even though we had mentioned it's 28, is we're keeping a little bit of buffer. Then you have binary weights, which is basically going to be used in the convolution. And you have binary biases, which we're using the randomize function to create the random uh, images which are going to be generated, which we'll be looking in the further slides. And you have the hardware design. Now, the hardware design typically consists of three major source files, which is going to be a LeNet.cpp and test.cpp and LeNet.h. And all of them are going to work together and give us the predicted outputs, which we'll be looking in the further slides. So let us now start off with LeNet.cpp. That's your main source file. So starting off with, as you can see, so you have a MAC function, which is multiply accumulate. So basically it performs the key operation for a neural network, multiplying two numbers and adding the result to an accumulator. And what is the purpose of it? It's basically used for use in convolution and fully connected layers. And you also see that there is a pragma HLS inline used. This ensures the function is inlined for reduced overhead. And then you have convolution layer with ReLU activation. Basically, it applies convolution filters to input data and adds a bias, followed by ReLU activation function. And you have inputs, which is input underscore 771, which is your input feature map, filter 771, which is filters are kernels for convolution, bias for each filter. Now, each of these variables in this code is added with the last three digits of my tower ID, which is 771. And why is that? Is to make sure that this code is mine and it's my work. So what operation takes place in this convolution layer with ReLU function? It iterates over each filter, applying it to the input using a sliding window. Accumulates results are stored in mac underscore 771, and the function which is used is nothing but max of 0, x. Right. Now you'll also see that we've also used the Plasma HLS pipeline here, which is basically ensures loop pipelining for improved throughput. Now you have your max pooling layer. So basically, this reduces the spatial dimensions by dividing input into non-overlapping regions and selecting the maximum value from each region. The purpose of this is downsample feature maps, reducing size and computational complexity. Then you have your softmax layer. Sorry. Yeah, you have your softmax. I don't think before softmax layer, you also have a fully connected layer with ReLU activation. So here it basically performs the matrix multiplication between input and weight matrices and adds a bias to it and applies ReLU. And purpose of this is to connect all input features to all output neurons for classification. In your softmax layer, in the softmax activation function, basically it converts raw and output scores into probabilities and ensures output sum to 1, making them interpretable as probabilities. Then you also have full forward pass. This is which you can see here. Basically, here it ensures the LeNet forward pass in sequence, convolution, pooling, and fully connected layers. And so that's about basically the LeNet.cpp is mainly used for HLS optimization directives. And you have your data types here. And then you have your intermediate results. It basically uses arrays to store the intermediate outputs for each layer, ensuring modular processing. And you have customizable parameters like you have image width and image classes, which is of variable dimensions, which we'll be seeing in the next program. Then are coming to you have your LeNet.h and test.cpp. So LeNet.h is basically where all your header files are declared. As you can see, you have your defined LeNet underscore h, and you have your apfix.h. And basically all your function units are also defined here. And as you can see, we've defined the image width and image height as 32 into 32. And your num class is 10, function units 120, function units 2 was 84. And your test.cpp is nothing but your test bench where all the inputs are passed on for you have basically sample input. And as you can see, we've also initialized hashtag include stdlib, which basically we're using for rand function for randomize, where the values are randomly generated for the images from the pre-given data set. So results. So this is your results. So you have simulation result is captured after executing code. This is how it is. So this is your simulation done is with zero errors. Now also this particular code has been run on Vivado with different boards taken into consideration. That so you have Zing 7000, you have RTX 7, and then you have Vertex Ultra Scale Plus, and you can see each of them how the performance takes place. Uh, Vertex Ultra Scale Plus being the best out of the lot. And there are different graphs on how each of them are working in ReLU, linear step, and different activation functions. And in Vitis, when you simulate and synthesize it, this is how the core logic is. It gives the latency for it takes about 58,000, sorry, 82,525 cycles, and you have 12 BRAMs, 89 DSPs, 13,043 flip-flops, and 13,421 LUTs generated. And your resource utilization breakdown is here. So you can see that LUTs take about 45.18%, flip-flops just take about 4.06, DSP takes 50.76, which is the highest. And clock frequency, so your target is 30 clocks, but then your estimated is about 18 clock cycles. And then you have your flip-flop versus LUTs in terms of various table, MSPs, as you can see here. So what is the outcome? So, and what's the future scope is, so we successfully implemented the LeNet 5. So the architecture was effectively implemented and debugging using Vitis HLS, ensuring that design runs optimally on FPGA platforms for real-time image classification tasks. So optimized for FPGA with Vitis HLS, a network was fully optimized using Vitis HLS to exploit FPGA's parallel processing capabilities and leading to a reduced latency and improved computational efficiency compared to our basic CPU implementations. We had modular testing of core layers, which is the design successfully tested the convolution, pooling, fully connected layers in a modular architecture. Scalability with larger data sets. So while the current design uses only MNIST, the architecture is designed to scale. The future work can explore the use of larger data sets such as CIFAR, CIFAR 10, or ImageNet for more complex tasks or more complex image recognitions. And we've also enhanced the model with random weights. For further experimentation and performance evaluation, the system can include a broader range of random weights and bias values to test the robustness of the network in different conditions. And in future improvements, future iterations, what can be done is design could explore integration, additional optimizations for even more resource constrained FPGA platforms and further testing in real world image data sets. And the performance basically of hardware accelerated inference can be enhanced by exploring advanced techniques such as quantization and model pruning. Now we'll look into so this is the code and which is simulated in Vitis. So this is your lenet.cpp, lenet.h, test.cpp. So this is how it is when we run the simulation. It shows that the simulation is done with zero errors. Predicted digits is 2. So with the input which you're given, the digit is 2, which is predicted. You have your synthesis here. This is how your synthesis is going to look like. And you have your various. So this is the target device that you have seen, XE7K70, 70T. You have your other ports, top level control, top function arguments, mapping. And basically this is our final report, which I will be attaching in the zip file, which you get free to take a look at. And that's about it. So this is our implementation of our project of mini project 5 using LeNet 5 implementation. Thank you.